Classifying numbers. When was the first time you heard about numbers? You probably learned to count from 1 to 10 at a very early age, but since then you've encountered a variety of different types of numbers. List some examples of all the different types of numbers you have seen. Search your memory for some of the more obscure ones. So I'm going to pause, I'm going to write down a bunch of numbers. You should pause, you should write down a bunch of numbers. We'll meet back here and compare. Okay, so here's my list, and you can compare that to your list. So look, there's pi. We met that pi in measurement, right? Here's fraction, 3/4, a decimal, some negative numbers, radicals. We've seen those before. Repeating decimals. Something we're going to get introduced to a little bit later. And a fraction. Mathematics groups numbers into various types. Here's how mathematicians classify numbers. We have the natural numbers. Natural numbers are the counting numbers. 1, 2, 3, 4, and so on. And 3 dots mean and so on, right? Continue in this pattern. Whole numbers adds in nothing. Well, that's not true. It adds in 0. 0, 1, 2, 3, and so on. Integers. Now we get into the temperatures we're going to be entering soon. So negative numbers, -3, -2, -1. 0 is included as an integer, and then into the natural numbers. So from the negatives through the wholes and into the natural numbers. Rational numbers, which uses Q for a symbol. Here's so N for natural, W for whole, I for integer, Q for rational, because R is reserved for real numbers. The set of all numbers that can be expressed as a fraction, A over B, where A and B are integers, and the denominator B is not 0, because you're not allowed to divide by 0. So here's a rational number. 3/4. Here's another one. 2/3. Here's another one. 5/1. Q bar. The bar in mathematics means not. So the irrational numbers are not rational. This is not Q, right? The set of all numbers that can not be expressed as a fraction in the form A over B, where A and B are integers, and the denominator B is not 0. So pi is an example of an irrational number. It cannot be expressed as a fraction. Root 21 is an irrational number. 1.01, 001, 0001. Shouldn't be a comma in there. There's no comma. And there's no 1. Dot, dot, dot. Okay, dot, 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 meaning, and so on, continuing onwards in that pattern forever and ever. And lastly, the real numbers, that's the R. So the R is reserved for real numbers. The union of the sets of the rational and irrational numbers. So that's rational numbers and irrational numbers together. Okay. Next. Note that all of the natural numbers are in the set of whole numbers, and all of the whole numbers are in the set of integers. For example, the number 4 is not only a natural number, but also a whole number and an integer. We say that the natural numbers is a subset of the whole numbers. That actually in mathematics looks like this. Natural numbers is a subset of the whole numbers. You don't have to know this notation, okay, but you may see it in your mathematical travels, which in turn is a subset of the integers. The whole numbers are a subset of the integers. We can represent the relationship between the natural numbers and the whole numbers in the diagram below. To this, we're going to add the set of the integers. So integers encompass, right? But they include the negatives, which aren't included in the whole numbers, which includes a 0, which is not part of the natural numbers. And we're going to come back to this diagram again and again. The number 4 is not only a natural number, but also a whole number and an integer. Is the number 4 also a rational number? That is, can you express 4 as a fraction? Yes. How? You put it over 1. So now it's a rational number. It's of the form a over b, where b is not 0. Can every integer be expressed as a fraction? Yes. Write them over 1. And they will become fractions. So you can have negative 10 over 1. It's a fraction. It's a rational numbers. So is the set of integers a subset of the rational numbers? Is every integer also a rational number? Yes. Integers is a subset of rationals. The Q's. You don't need to know this notation. You'll never see it, not in 10C. Go back to your diagram in 1 and add in the set of rational numbers. Okay, so the rational numbers. Q. Now, number 4, rational numbers were described as fractions, but they can also be described in decimal form since all fractions can be changed to decimals. How is this done? Division. On your calculator, 3/4 means, follow the calculator. On, clear. 3/4 means 3 divided by 4. Enter, and that's a decimal, 0.75. So that's how you do it. You divide 2/3, 0. Well, here, let's do this here. 2 divided by 3. Enter. 0.666666667. Your calculator's rounding the last decimal place here, right? That's a 7. So really, it's 0.666 ... showing the pattern repeats, or more properly, 0.6, and we put a bar over the repeating part of the fraction, and this just says the 6 goes on forever. And you also could have done 0.6 ... just showing that that goes on. But I always like to put a few, right? Let's just see what the pattern is, and then we can see it's going on, or when you see the bar. 1/9. 1/9. Bunch of repeating ones. So 0.1 repeating. This is preferred notation. At least I prefer this notation. 3 and 7/11. 3 and is plus 7 divided by 11. Don't worry, calculator will do order of operations. It will divide, then add 3. 3.63636363. 3.63. This is a repeating decimal with a period of 2, right? It's repeating with 2 decimals. Repeating, that's this. What kind of decimals are these? They are called repeating decimals. The 6 repeats, the 1 repeats, the 6/3 repeats. Convert the following fractions to decimals. Okay, I'm going to rely on you using your calculator. 4.25. You should probably pause and do these, right? 0.1875. Somebody once said, and I got to look up who, mathematics is not a spectator sport. You learn math by doing, not by watching. Go to a football game, it's a spectator sport, unless you're a player. So you can watch, but if you're a player, then you do. And 2 3/5 works up to 2.6. Now you'll notice no repetition. And when it doesn't repeat, we say that it terminates. It ends. So they terminate. So when a fraction is changed to a decimal, the decimal either repeats or terminates. Use your patterning skills to determine. Show some work. We want to know why. So just giving me the answer is not going to do it for you here, right? Determine the 50th digit of 1/13. So 1/13, calculator, clear 1 divided by, I feel like I'm using a defibrillator, clear 0.076923. Guess where I am? 0.076923, 0769. So it's going to continue in that pattern, right? So what do we have? 0.076923, and then it starts repeating. So this is how we write it. This is what repeats. We have 1, 2, 3, 4, 5, 6 decimals repeating. Right, there's 6 of these. So if I write out the next set, 0, 7, 6, 9, 2, 3, then we will have a total of 12. And if I keep going, 0, 7, 6, 9, 2, 3, then we have 18. So we want to figure out, well, if you've got 6 repeating, how many 6s are there in 50? 50 divided by 6 is 8. And something, right? I mean, what's left? 8 and 1/3. So if we have 8 groups of 6, that's 48, right? 8 groups of 6 is 48. So the 48th will be a 3. The 49th will start over again at 0, and the 50th will be the 7. So there's the 50th, right? So what do? We've got the size of the repeating group is 6. We want the 50th digit. 50 divided by 6 is 8. We have 8 whole groups. 8 times 6 is 48 with a remainder 2. I mean, really, you might want to write this as 8 remainder 2. And this remainder of 2, 1, 2, takes us, this will be the 49th decimal, 50th decimal. And let's go over here and say the 50th digit is 7. Determine, work shown, right? Work shown, we've shown some work. Oh my God. The following are examples of irrational numbers. Remember, that's the Q with the bar meaning not rational. Use a calculator to express the last 2 in decimal form. Root, that's clear. Clear, second, root, 12, enter. Okay, what do we got? 3.464, 3.464, 101, 101.615, keeps on going. Pi, calculator. Second, pi, and then hit enter and you get the decimal. So pi equals 3.1415926535897932265. 847264643383279502888. There goes the phone, so I better stop now. Okay, phone call dealt with. Now, if you look at pi here, you see, notice it goes 264 because it's rounding, because the 3 is followed by a 5. So you're always getting a rounded value there. But how do these decimals differ? They do not terminate. So we will use fancy words and we will say non-terminating. They do not repeat. So we will say non-repeating. They do not repeat. They do not terminate. Can a number be both rational and irrational? Can you terminate and not terminate? No. Can you repeat and not repeat? No. So you cannot be both rational and irrational. That applies to people as well as numbers. Go back to your diagram in question 1 and add the irrational numbers to the diagram. Okay. Go back. Here we go. Now, that means I'm going to have to separate off. All right, so we're going to draw ourselves a little box here. going to make a new box here and put a Q with a bar over top. So these are the irrationals. This is not to say that the set of irrational numbers is smaller than this set. They're both actually infinitely large, although it might actually be different infinitelies, but, well, or infinities. You can actually look that up. There's different infinities out there. There's countable and non-countable, and that's not a topic for us. Complete the following table. Put an X in the number if it belongs to the set. You may put as many X's as you need. In the last column, name the set of numbers that best describes the number. And that set will be the most restrictive. So if it's natural, then we're going to say it's a natural number. If its most restrictive is an integer, so its leftmost set really is what it's going to be. The best description will be the leftmost set. Okay, I'm going to go fill this in. This probably doesn't fit on a page. No, of course not. So I'm going to fill this in, and then I'm going to come back, and then I'm going to slowly scroll through it, pausing enough such that you can pause and look at it, you know, all the way down and check it with yours. So, okay, fill in time. Huh? Fooled you. Okay, let's do the first couple together. So -2, not natural, not whole, it's an integer. All integers are rational. You can't be both rational and irrational. The best description is that it's an integer. -16, all right, same deal, integer. All integers are rational. Anything, you know, anything natural, you know, then you start moving up the sets. If it's natural, then it's whole, then it's an integer, then it's rational, and so on. Best description for this is an integer. 9.2, well, that's not natural, nor is it whole, nor is it an integer, but it is rational. And remember, that's a Q. 2/5, 0.4, also just rational. Q. All right, let's just do this. Root 20, it's irrational, and that's a Q with a bar. Root 9 is 3, so it's natural, and it's whole, and it's an integer, and it's irrational. But the best way of describing it is its most restrictive set, which is natural. Just to describe it any other way would be unnatural. Pi, irrational. Q, not Q, right? Q with the bar. 0. No, I forget. Okay, right. It's whole. 0 is a whole number. All whole numbers are integers. All integers are rational. We're not going to describe it as rational or integer. We are going to describe it as its most restrictive set, which is whole. -4 1/3. It's an integer. Well, no, it's not an integer, right? So it's rational. And that's the best way to describe it. 28, natural, whole, integer, rational, natural. 0.12, repeating decimal. A repeating decimal is a rational number. 3.14, this is not pi. This is 3.14, and it's a terminating decimal. 4.25, 255, 555. So we've got 1 5, then 2 5, then 3 5s, and then it'll be 4 5s, and that's just not rational. So it's irrational, Q bar. 4.83, repeating. A repeating decimal is rational. 16/7. Well, that's not natural. It's not natural, it's not whole, not an integer, it's rational. And that's a Q. And 48/6, well, hey, that's just 8. And so if it's natural, then it's everything to the right, but you cannot be both rational and irrational, just rational. No, kidding, it's natural. Okay, feel free to pause at any time. You can scroll back up, or I can scroll back up for you. And then I'll come back down. And if I messed any of this up, let me know. Number 9, which will be a nice 9 on yours. And all natural numbers are whole numbers, but not all whole numbers are natural numbers. Matter of fact, there is only one, the only whole number, 0. It's the one that looks like a whole. See, whole, H-O. Likewise, all whole numbers are integers, but not all integers are whole numbers. Name 3 integers that are not whole numbers. How about Fred, Wilma, no, we have to name. So -3, -2, -1. Basically, the negative integers are not whole numbers. In the following diagram, shade in the section that represents all integers that are not whole numbers. Okay, let's see how well I can shade. So if they were whole numbers, you know, like 1, 2, 3, 0, etc. So this is shading in. Basically, this area that I'm shading or attempting to shade is the negative integers. All the other positive integers are actually included in here, and then 0 is in here. Name a rational number that is not an integer. What types of rational numbers are not part of the integers? So, you know, how about 2/3? There's a rational number that is not an integer. Or 3/4 is a rational number that is not an integer. What types? These are the decimals, right? And they either terminate, like 3/4, or repeat, like 0.66666. Keep going forever and ever. So let's place the numbers in question 8 in the appropriate section in the diagram below. Now you notice that this box, okay, so we start with the natural, most restrictive set, add on the wholes, which is only the 0, and there was a 0 in the table, so let's put the 0 in there. And then the integers, and then all the things that are rational but not integers are out here. Irrationals in a separate box. Take them both together. The union of those two sets is the real numbers. Okay, so we start at the top with -2. And remember, we shaded this. This is the negative integer section. -16, 9.2, rational, but not an integer or anything. 2/5, also rational. √20, irrational. √9 is 3. That's natural. Pi, irrational. 0, already put the 0 in there. -4 1/3, rational. Negative, but not a negative integer because of the 1/3. 28, naturally. 0.121212 repeating, rational. Since it's a repeating decimal. 3.14, rational. That's not pi. That's rounded. You will never use this for pi other than on that one worksheet, which is from like junior high, so we kind of ignore that. 4.255252525. There's a pattern here, but it's not repeating, right? Because next would be 2 and then 4 5s and then a 2 and then 5 5s. 4.83 repeating, put you over here, 4.83. And you notice it's the 3 that's repeating, not the 8. This is not 838383. It's 4.833333333333333, 16/7. And 48/6, naturally, because that's equal to 8. Oh, we're done. Yay.